Atchison here, and we finally made it out of vision. We're into sound. We do have other perceptual abilities outside of vision. And so while we talked about those and we talked about all that, we're going to move on to other dimensions, and we're going to start on hearing. Specifically, this lecture is going to talk about sound in the ears, where this is the first lecture for chapter 9 about sound. So I've linked this video for you on Canvas, and it's also on the YouTube playlist. And what's really neat about this video is it shows you what sound looks like. It tells you in the middle how they get these pictures of what sound looks like, but it's great because it shows you that sources of sound are initiated by this movement that disturbs the air molecules. You can see the air molecules move in these videos, which is really, really nice to see. And you can see this air collide with other air molecules, resulting in this change of pressure that moves outward from the source. And what's also really nice is you can see that these things grow continuously larger. You can see this really nicely with this picture that's a screenshot of the video, where that sphere gets continuously larger. So at the speaker in the middle, it's a lot smaller sphere, but as you move outward from there, we get a lot larger. Now, how we talk about sound, this air pressure in a sound wave, a lot of the stuff we're going to talk about pure tones, which are just like a pitch, like a tuning fork. When you hit a tuning fork, it's going to make a pure sound. And how we talk about sound and how we measure sound, we do using these cycles. A cycle is this repeating portion of the wave. And the way we measure it is we measure it from normal air pressure level to its maximum, back to its minimum, and then back to normal. And that's what we're going to consider one cycle, where we go from normal to max to minimum and back to normal, that one cycle. And what's interesting about these pure tones and how we measure them is we'll look at several different things. We'll look at the frequency of that cycle. How often does that cycle repeat? And we also look at the amplitude of that cycle. How tall or how short does that cycle get? And we'll also talk about the complexity of it. Is it a pure tone, or are there multiple frequencies on top of each other? So frequency corresponds to our perception of pitch, okay? The lower frequency has what we're going to perceive as a lower pitch. So here you see that these cycles don't repeat as often, and you're going to hear that as a lower pitch. When you heard the scales, when it was the lower end of the scales, that was going to be a lot lower frequency. When it got to the high end of the scales, it was going to be a high frequency, a higher pitch sound, where that cycle repeats more often. Amplitude is again it corresponds to our perception of loudness. Here are some examples. So a high amplitude sound, something that's loud, is going to have a lot taller kinds of sound waves, okay? Whereas a low amplitude, a soft sound, is going to have a lot lower amplitude. Here's an example of that. So you could hear the loud sound is going to have a lot higher amplitude. The soft sound is going to have a lot lower amplitude. So the difference between thunder and rain. That big clap of thunder is going to have a high amplitude wave, whereas that soft sound of the rain is going to have those low amplitude. And complexity is again about, and this goes to our perception of timbre, this difference between a pure tone or a mix of frequencies. And this also, we see this as resonance as well. So here's an example. So that's a pure tone. This is just that normal curve that we're going to be talking about, where a complex sound is going to be a mixture of frequencies and a mixture of these things. Here's an example. You could hear there was a lot more going on there than there was with that simple pure tone. And again, that's what we're going to talk about in terms of timbre. So again, frequency is that physical dimension of that sound wave, where pitch is that perceptual dimension of how we're interpreting that physical stimuli. So the frequency of a pure tone is that physical dimension, how many times that sound, that cycle repeats itself over a time period. And we measure that in terms of hertz, okay? So hertz is literally the number of cycles per second of a sound wave. So the more that cycles per second, the higher pitch it's going to be, and the less times it cycles per second, the lower pitch it's going to be. The typical human sound detection range is about 20 hertz, so that's going to be repeating 20 cycles in a second, up to 20,000 hertz, and that's going to repeat 20,000 times a second. So that, again, that wave, that cycle, this is how many times it repeats. This YouTube video that's also linked on both the YouTube playlist and on Canvas allows you to kind of listen to this whole range, okay? I will warn you that at the end, YouTube kind of cuts it out. I think YouTube only goes to about 1750 in terms of hertz, so 17,500 in terms of hertz. So it'll cut you off before you get to the full 20,000. What's interesting, though, is when you do this with a group of different aged individuals, and you say, raise your hand when you start hearing something, and put your hand down when you stop hearing something. When we get to those high frequencies at the end, we'll see that older individuals tend to put their hands down sooner than younger individuals. And this has to do with the fact that there's age-related hearing loss. When I do it with in a lecture with 120 18-year-old freshmen, I definitely put my hand down before they do. And this is, again, because of that age-related hearing loss. And so things like the cell phone sounds that sometimes teenagers will use in classes where they can hear it, but their teachers can't, are reflections of these age-related hearing losses, this differences in high-pitch frequencies versus low-pitch frequencies. Also, people will, if they don't want teenagers to loiter outside their business, sometimes they'll play these high-pitched sounds to keep the teenagers away, but their normal customers can't hear them. So it goes both ways. This taking advantage of these age-related hearing losses. Sometimes it's called the mosquito tones, things like that. So please watch that video and go through it. It's interesting. So another physical dimension that we talk about is amplitude. So we talked about, again, that's the loudness. Again, amplitude is that physical dimension, where loudness is that perceptual dimension. Amplitude is the difference between the number, the maximum, and the minimum, okay? So how different is that height between the maximum and the minimum? And again, this is what we perceive as loudness, and this is measured in decibels. So that's something, a sound term that you're probably somewhat familiar with. I know I use it when I'm looking for headphones for my daughter. I want them to cut off at a certain decibel level so she can't turn them up too high, so she can't hurt her hearing and exacerbate that age-related hearing loss. Loudness is, again, that perceptual dimension of sound that's, again, related to this physical dimension of amplitude. And this is what we're going to comment on is how intense or quiet a sound seems. So again, that's that perceptual dimension of loudness from the physical stimuli of amplitude. So an audibility curve is really just the absolute threshold to hear a particular frequency, okay? And here's an example that's from your textbook. You see that these lower frequencies, you're going to have a lot higher sound, a lot higher amplitude to be able to detect it. So this line is essentially is an absolute threshold. This is showing you exactly kind of where this absolute threshold is. And auditory sensitivity is really maximum. You can see this. We can really hear these quiet sounds at very low decibels between about 500 and about 5,000, which really corresponds to human speech. So there's an an activity from the National Institute of Health that I want you guys to do. It is your participation assignment today. So please do that. It allows you to kind of play with this dimension of how you can hear a particular sound and how it will sound louder, even if it's the exact same decibel at a higher pitch. And so it allows you to kind of play with this relationship between frequency and amplitude, this relationship between loudness and pitch. So please do that, and there's some questions for you to answer. You're also going to be able to do an equal loudness contour in this NIH activity. So there's two separate ones that I have assignments for. One of them is for the pitch and loudness, and this other one is on this equal loudness contour. And an equal loudness contour is essentially just a curve, and these are a whole bunch of equal loudness contours. There's a bunch of different ones of these. These are audibility curves. It's a whole bunch of it, and it says that basically you get different information. Something's going to sound equally loud at different pitches, and you're going to be allowed to kind of do that on your own through this activity. It gives you the step-by-step instructions on how to play with these sounds so that you can graph them yourself and see kind of your particular equal loudness curve for certain sounds. And again, human hearing is really best between the frequencies of 500 and 5,000 hertz. That's when we're most sensitive. And then we have a lot harder time hearing when we're above 5,000 hertz or we're below 500 hertz. So we're not going to be as sensitive to those. And again, this whether it's a chicken and an egg thing, whether human speech is in this range because it's what we hear best, or it's what we hear best because it's the range of human speech, hasn't obviously been figured out. But we do hear best in this range, and this is also coincides to human speech. Complex waveforms, again, don't sound like pure tones. That was the difference of, that pure tone versus that more kind of verbal, vocal melody that we were given. High quality, they have a sound quality that depends on both frequency and amplitude, and their fundamental frequency. So when we measure the frequency of something, if we're measuring the pitch of your voice, I'm going to get a fundamental frequency rating on that. That's what I'm going to call your pitch. So if you have a higher pitch voice, your fundamental frequency is going to be higher than if you have your friend who has a lower pitch voice, they'll have a lower fundamental frequency. When we measure speech and we look at the differences in how people talk, we'll give that kind of information about the fundamental frequency. That's kind of what we use to measure pitch. Now the problem is complex waveforms, like speech, have more going on than just this one pitch. It's not a pure tone. And so we'll talk about that dynamic here in a second. So sounds that differ in timbre. So these are all different vowel sounds. So we have heed, like you would say in heed. We have as you would say in father, and we have oo, as you would say in who. And this is kind of shows this harmonic content of these different vowel sounds. So the harmonic content is the idea that there's more than just fundamental frequency going on. So fundamental frequency is the first harmonic, but that's not all that's going on. We don't speak in pure tones. We speak in a variety of harmonics. So this shows kind of the different harmonics that can be in each one of these. And these are done with a male voice. And so again, these complex sounds that have the same pitch and the same loudness all don't often sound the same. And this has to do with the differences in their harmonics, the differences in the amplitudes of these other tones, these overtones, outside of just the fundamental frequency. So their fundamental frequency is kind of our baseline. Pitch, it's the biggest pitch, it's our first one, but then the other ones are still there. And only overtones within our human range of hearing contribute to timbre. So ones that are outside of that don't. And we see that low amplitude overtones contribute less to timbre than the higher amplitude overtones will. And again, these overtones just sound like what they are. They're on top of, they're tones over on top of fundamental frequency. And again, fundamental frequency is going to be that basic. How we start to look at these is something that we call Fourier analysis. So this black line would be what the sound is actually being graphed at. And what Fourier analysis says is that this is going to be able to break that apart into the different pieces of it. So we can see the different components of sound, the fundamental frequency. Here is our red line. It's our first harmonic. And again, if this is speech, we would say that fundamental frequency of here of about 100 hertz would be our pitch. That's what we would say is our pitch of that tone would be this. And so if you're a musician, which I am not, so I may totally mess this up. When you play a note, the fundamental frequency is that note that you're playing. But the idea that it's more complex than that takes into account the second and the third harmonics. And again, the Fourier analysis is a way that we can start to look at these different harmonics. We can look at these different pieces of the puzzle that make up a complex waveform. What's interesting about timbre, though, is that you can take a sound and you can remove the fundamental frequency, and the pitch is going to sound the same to you. It's going to sound very, very similar, which is interesting because the fundamental frequency is primarily what your auditory system is using. What's interesting about this illusion of the missing fundamental is it shows that more is going on than just this one pitch piece of fundamental frequency, that it's really these complex patterns are being used to determine pitch. And with this is really indicative, we can really see this with timbre. So you can kind of think back to kind of the visual system where in processing faces, you could look at it from both a modular and a distributed way. You could say it's mostly being done here in this one module in the fusiform face area. But we also saw coding happening and these same patterns of neurons firing in the brain that were indicative of just for face processing. It's the same kind of idea that we're able to detect these things both through this main conduit of fundamental frequency, but also these other patterns that are related. So pitch perception is more than just fundamental frequency. So that ends our discussion on sound. Thanks, and talk to you later.